So I'm going to start it off and just kind of give an overview for the installation, Marine Corps Air Station Miramar in San Diego. Mainly we want to talk about renewables and how it relates to microgrids today. And so there's two microgrid projects at MCAS Miramar. And so to kind of distinguish those, Scott is going to talk about the one on the right, which is a battery storage and PV 100% renewable building level microgrid. And so this project is complete, demonstrated, we're done. Scott's going to talk about all the technical stuff with that. It was an amazing project, the most fun I've had in my career for sure, my short career. And the installation microgrid on the left is a $20 million capital investment to make the entire installation's critical load an island. And so this includes over 100 mission-critical flight line facilities using both renewable and conventional fuel. So I'll get into those details later, but let's turn it over to Scott for the technical stuff.
It's on. Can you guys hear me?
I actually forgot a slide.
Oh, you forgot a slide?
Sorry. I'm not too prepared. Sorry about that. So to not confuse the two different organizations doing the two projects, Scott's from Raytheon over here, and these are the organizations involved with the battery storage project that was a ESTCP demonstration project, if you're familiar with that program. On the left, this project is a joint venture between Schneider Electric and Black & Veatch, and that project was in the Energy Conservation Investment Program from the OSD. And in both projects, we've been lucky enough to have NREL involved in both of those every step of the way.
Cool. I got the... So I got involved with this project back in about 2012. The scope here was to install energy storage in order to cover a couple use cases at Building 6311 at MCAS Miramar. The battery chosen was a zinc bromide flow battery, spec'd at 1 megawatt hour, and we were also using existing about 230 kilowatts of PV, carport PV installed on the base, and integrating that existing hardware with a microgrid controller that we developed to perform both islanding, so the ability to isolate from the utility and work off-grid using 100% renewables, and also peak shaving to offset the peaks of the building. And so this was a demonstration project. The power levels were about 100 kilowatts peak, more or less, with the 20 kilowatt base load. And so you can see an example down there. So the let's go to the next slide here. So the operational overview for the islanding scenario is when a grid outage would occur, our IPEM C2, which Intelligent Power and Energy Management microgrid controller, would detect that and then manage the energy storage and PV to first disconnect the building from the base grid, then bring the energy storage up in black start, so have that start providing voltage and frequency, excuse me, and then bring the solar PV online, so that would synchronize with the battery as if the battery were the grid in this case. And so what our main use case was maximizing the amount of PV penetration to keep the battery demand as low as possible, and thus extend our islanding time. And so the idea is to keep the critical load in the building on. There's also a follow-on to this project where we integrated HVAC load shedding, so we could reduce the HVAC demand on the building, which was by far the highest consumer of power. So part of this project, we partnered with NREL at their ESIF facility, the Energy Storage Integration Facility, which is a state-of-the-art lab where we brought our controller, some of the equipment, and then Advanced Energy had 2 of their PV inverters that were installed there, and we were able to do a full-scale power hardware-in-the-loop testing. We spent about 6 weeks down in Golden, and we worked with some of their engineers to do basically simulate all of our use cases at full load. So disconnecting from the grid, reconnecting to the grid, introducing a lot of reactive power to make sure that because this is an entirely inverter-based microgrid. So adding a lot of those transients, destabilize that. And so there was a lot of things that we found out during this event that was incredibly helpful. Some of the questions that we addressed were the black start sequencing. So when the base grid went down, how do we sequence all of the different pieces of equipment to bring them up and have a stable microgrid for the duration of the islanding? Do the anti-islanding algorithms destabilize the battery inverter, since it's essentially like pulling on that inverter to see if there's a stable grid presence? How much PV penetration can we push without destabilizing the microgrid? Which was interesting in this case. We found that without the actual battery side of things, we got 100% PV penetration. But when we introduced that battery, the DC components, we got about 80% stable. And then how does the system respond when we're doing things like PV curtailment, and how is the power quality of all the inverters involved in the system? So in October of 2015, we commissioned the system. You can see there is the battery from Primus Power, and then the carport solar, and then building 6311 in the back. So we did a couple of demonstration events here, and so you can see some of the actual data from that. And so this is the second islanding demo. The first one was really just to make sure, is this working? Anything really bad going to happen? And then in the second one, we started introducing the real interesting thing. So you can see in the very beginning here, we're charging the battery. So this is the energy being pulled from the grid. Right about here, we disconnected. So you see that that flat line there, which is the amount of energy that's being drawn from the utility, and the amount of power that the battery is providing is going to be this gray line over there. And then at about this point, we turned on the PV inverters and started curtailing them. So they're actively following the load in this case. So they're going to be maintaining as much of the building load as possible, and then the remainder of that is going to be supplied by the energy storage. Interesting things that happened here in San Diego. The sky is usually perfectly clear. If you look at the PV generation curve, it's like the smoothest curve you can imagine. But on this day, we actually had clouds enough so that it occluded the array, so that we had these cloud edge events that would completely take down the PV inverters and then have them come back online, which was an interesting use case for the battery, because the battery was able to hold up to those like serious transients for basically a full load drop and then recovery. So our third islanding test, you can see this data looks a little bit different. Based on some things that we learned from the previous one, we were able to modify some of those curtailment algorithms to make the battery usage almost entirely flat throughout the entire course of the run. And so you could see that in this case, the average building load here was about 77 kilowatts, and then the maximum PV penetration that we reached was 81.5%, which is pretty significant. Another interesting thing that we added to this project was the ability to curtail the HVAC loads. And so some of these big load steps here you can see is when we did a level 2 load curtailment, which was essentially just running the fans, not running any of the compressors. You can see these big drops in power here. So the cooling load is a big contributor, and when that was reduced, and we were able to reduce the effective load of the building on demand. So this was about, I think, 6 hours from start to finish. And we had a bunch of people in the room. So this was a demonstration for ESDCP, which was the organization that funded us.
So this was a really exciting day, because we invited people to come witness the event. And so we had about 50, 60 people crammed into a conference room, people pouring out the door, and we actually shut off the lights and the power to the entire building, with 100 government employees inside, and really simulated an outage. And then within 5 minutes brought the power back up. And the whole rest of the day, people were on 100% renewable energy. And most people didn't know it. And you think that's, not so good behaviorally, but technically it's a good thing. People didn't really notice that they were under renewable energy. And so it was really interesting having different types of people from the community come in, and technical people, and just doing an event like this was pretty interesting.
So during the event, we have two user interfaces that we developed in order to show people what's going on. So this is the first one here, which is basically a system overview. Shows you, what your current load is, how much of that load is being supplied by your carport PV, what your PV penetration is, battery stats, all that kind of stuff. And this was, up live and updating. And there's also a lot of functions here where, the energy manager can connect or disconnect from the grid, manage some of the states for the equipment, look at faults, that kind of thing. And I think the more interesting one is part of the scope was to develop a public utility awareness display for building tenants, so they can see exactly how their behavior impacts the energy usage for their site. And so we went back and forth a lot trying to figure out what's meaningful to someone who's actually sitting at their desk doing work. How do you convey if you do this slightly different, then this is the impact on the building usage. And what we came up with was, if you think about how a building, how a load looks throughout the day, is you have pretty flat at night and in the morning, and then people start coming in, you get a peak, and then that goes away. And the way that they characterize buildings over the course of a year is with Energy Star, but if you just pick a flat, a constant level, you're going to be, surpassing that in the morning, and you're going to be, failing in the afternoon. And so what we did is, so in this usage dial right there, is that green line there will change throughout the day. So anyone who's walking by can see oh, it's 9 a.m. in the morning. This is what our building usage should be in order to meet our Energy Star target of 75 or whatever it is that you would configure here.
So this is kind of my proudest thing that Scott has done for us, because we spent a lot of time together working this out, and he did all the math to make it work. But the innovative part here is that the green means that you're efficient, and the red means that you're not being efficient. And so green and red on a HMI can mean a ton of different things. But I think what we did here was really innovative and important for just the layman's person in the building being able to walk by and know whether we're doing good or bad. And I would say that at this day and age, people still don't know what that means. I mean, people are still probably just looking at me like, what are you talking about? But we're coming from the ground up where some people don't even understand that the lights on the ceiling and the plug on the wall are coming from the same thing, and so I think we have a long way to go, but we're trying to have a good start here.
Yeah, so more things that go along with this is just tenant education. There's a whole learning center where you can learn about different aspects of the microgrid. And all this data here is updating real time, so you can see, the sun's out, your PV is generating. This is how my behavior is going to be impacting the system. And so there's a couple lessons that we learned from this. I guess the first one's sort of obvious. Testing each subsystem thoroughly eliminates a lot of bugs. There's a lot of things that we learned during this effort, and being able to go to NREL and integrate with that hardware offline, so we're not going to be interrupting power to the building and hopefully not breaking anything, was very valuable. The second one is, don't underestimate the amount of software required to make these systems operate smoothly. Integrating with a lot of different equipment, a lot of different interfaces, standards, even working with the utility company or regulation market. All of that you use software to communicate with, and making sure that integration is done early and rigorously is really important. And then if you have the ability to test the system without disrupting power, include that in your plan. Outages at Miramar, you needed 21-day advance notice, so if you had a last-minute change, you had to wait 3 weeks to try that out, essentially. And then renewable microgrids are achievable using only inverter-based generation, and advanced inverter controls provide new capabilities to existing PV installations. So utilizing existing solar on base is achievable in certain cases. And pass this back to Mick.
Okay. So I'm going to real quickly talk about the other project. We only have 10 minutes left, I think. So as to start, MCAS Miramar is an extremely renewable DoD installation. We're actually at 55% electric renewable on the installation. And if you talk about overall BTUs, I think it's about 35%. We're aiming to be 80% renewable electric by 2020 with another power purchase agreement. Most of our power is attributed to a 3.2 megawatt power purchase agreement for base load power from our landfill. I don't have a good picture of the installation, but on the south side of the airfield at the installation on Department of Navy property, there's a City of San Diego landfill where they extract methane, and there's 2 dedicated engines on a dedicated circuit to our base. And so that dedicated circuit means that we take that power, and it does not go out to the utility, which leads itself to be an asset to our microgrid project that I'm going to talk about. In addition, we have 1.5 megawatts of PV in distributed systems all over the base and a ton of solar thermal. This is a solar thermal system that's on our training tank, or otherwise known as pool. And that's a significant amount of MBTUs per year as well. So just seeing that picture of how much renewables are on the installation, this is a good representation, with the light brown being electric from the grid, or brown power, I would call it, and the dark brown being natural gas, and the renewables being the green in just total MPGs, what we're projected in the future. This says 2018, it's probably going to be 2019. So the installation microgrid project is something that we've been working on for a very long time. It's been in development since probably 2010. We just awarded it this year for $20 million. What it's essentially doing is taking all of our existing renewable energy assets, 1.5 megawatts of PV, 3.2 megawatts of landfill power, and building a conventional fuel power plant centralized on the installation that we can combine all those assets and use them for energy security at the base. And so the purpose is not to build a power plant that's going to take us off the grid indefinitely. That's not the point. We are a unique case where we're embedded in San Diego Gas and Electric territory, and we have pretty reliable power. But reliable power is one thing, redundant power is another. So this project will give us the ability to be completely redundant and power the flight line and all of its missions 100%. So in the DoD today, you have a lot of backup generators all over the place backing up different systems. This project is backing up over 100 buildings, 100% power. So essentially, this entire area in red can operate as if they didn't even know that the grid was out. Now, the purpose of this project is energy security, but the goals associated with it are to maximize the amount of the renewables that we have and their usage in an island. We learned from our last project that integration of renewables is extremely challenging, and using them in an island setting is going to, we're integrating renewables that nobody else has done in an island before. So this is definitely going to be a demonstration. And the last goal is something that I'm going to focus on, which is how do I make this thing pay for itself? Nobody knows because nobody's doing these things. So we're kind of trying to pave the way and make this thing provide us some money. So here's a look at that base and all the assets on the base. So the airfield is right here that's being covered by the microgrid. Pretty much anything south of this major road right here is covered. And we have a lot of PV and the battery in this area, which is also included. Lots of PV systems down here. And the landfill power comes from down here, and there's a dedicated transmission line into our circuit. The only other load, or the only other way the base gets power is from the top up here. On the north side of the base, there's one incoming feed from the utility. So we talked about resiliency, and for bases with 2 incoming feeds, that's an added level of resiliency, right? For us, we only have 1. So in that case, it makes it easy for us to disconnect from the grid. It's pretty centralized, but it lends itself to we need another redundant source to keep the flight line up. And so that power plant that we're going to build is going to be right at that incoming feed and basically feed the feeders. I'm not a technical guy, so I don't know how to say that well, that feed the entire base. So this power plant will be able to provide power wherever we want through control of switches at a centralized switching station. And we size the plant to be able to provide backup power to all of our critical facilities, but in the future we can always expand and really divert power wherever we want. And so here's what's really interesting, is the power that we're building is not a backup generator. What we're doing is we did a air permitting study to understand what we would have to buy in order to use these generators however we please. So what we're aiming to do is install Tier 4 certified generators, diesel generators, and best available control technology, natural gas generation. Both internal combustion, you'd say, why are you installing internal combustion this day and age with microturbines, fuel cells, and all that stuff? Well, the answer is cost and also reliability. These engines are not being used as our base load. Remember, our base load is renewable. We're already doing renewable. These assets are going to be used to take care of something else. So just like any other renewable source, the landfill has some challenges. So this is our base load of the base, just like a given week, just to give you an idea. So that green is the landfill power, and you can see how much of it takes up. What these brown spikes are the landfill dropping off. So methane content or the BTU content in the methane is not reliable. So what happens is that will drop off and kill an engine for a couple hours. And what that actually causes is a huge headache for us and lots of money. And it happens pretty often. I mean, this is just a given month, and you can see the red is the landfill dropping off. Although it's pretty consistent. You have days here where it hasn't gone offline. But your demand charges are monthly, right? So if that thing goes off anytime during a peak time during the day, once a month, I'm screwed. Right? So how do we solve that? This is a look at the operations center that we're going to be building for the microgrid. And it's basically going to be the energy office. The microgrid is kind of like the basis of your whole energy program. So I'm really looking forward to this field of dreams approach, where if I build this, I'll get employees. So I really don't even have, not even a supervisor at this point. So the energy world is changing, and I hope to change it more. So how we actually plan on using those generators is the natural gas, which we're going to be able to have certified to run 5,000 hours a year, is basically going to take care of our peak load during the day. We're going to use it for peak shaving. And given that it's going to be the cleanest natural gas generation that you can permit and install today, I would think that nobody's going to have too much heartache with that, considering most of our electricity in the Southwest comes from natural gas anyway. The diesels are going to be used for kind of emergency situations, for taking care of backing up the landfill. So if the landfill comes down for a couple hours during the week, we'll use the diesels in that time to save on our demand charges. And so in addition to that, we want to use the diesel for demand response, and I'm going to talk about that a little bit more. So here's another look at that operating picture, with the red being the diesel backup that takes care of when that landfill gas drops offline. And here's another picture that shows the natural gas engines coming in and leveling our load throughout the week and lowering our demand charges. So it's kind of an innovative way to use these engines for another purpose to make us money. And this is really what the future looks like for me, given that we're working on another power purchase agreement for more landfill power that is going to bring us almost 80%. This light green here represents that. And so over time, you can see that our grid is mostly green. And we're just using our conventional fuel to levelize the load to the utility, which helps them out and lowers our cost. So overall, SDG&E is 24% renewable in 2013. They're probably higher now, but nothing compared to 55% and hopefully 75% in the future. And so non-renewable, we're only going to be 20%. So this is my favorite, since we're on kind of a Navy panel here. I heard this from ASN McGinn years ago. He said, expand microgrid functionality for best return as opposed to just islanding. Microgrids are not just for islanding. In San Diego, my alma mater, the UCSD college that's right down the road from Miramar, Byron Washam is a pretty famous energy manager at that campus, and he said, microgrid needs to support the macrogrid. If we're just thinking about ourselves and islanding, we're missing the whole picture. And so that's what I'm trying to do with this project, but I'm currently coming up against resistance in California because California is super confused. They want microgrids, they want battery storage, they want everything, and they want no conventional generation. They want no diesel. So anytime I talk about using diesel and natural gas, they're like, no way. And there's actually limitations to using conventional fuel towards demand response. And that's a struggle that I have that I'm dealing with in California. And so here's what this picture would look like if we used our diesel for demand response. Let's say you called a demand response event on this day. We essentially bring our load from the utility down to nothing. And so that's, I see as a huge benefit to the grid. And for us, it means a whole lot of money. So if we can do all these things, we can save close to $1 million a year if all this stuff pans out. And what that means is I can sustain the microgrid that we built with the cost savings from it. And it makes energy resiliency something that's a lot more palatable for the DoD, and we can implement this at other bases. So I'm not going to read those, but I promised you a Top Gun slide or a Blue Angel slide. Thank you. Let's leave that up. I don't know. You probably don't want to read this. You probably just want to look at that. The air show is this weekend if anybody's going to make it out to San Diego.